All right, so in this video, I'm going to talk about section 1.4, which is all about the matrix system here that you see, where you have the matrix A multiplied by the vector X, and that's going to equal to the vector B. Okay, so obviously here, right, we have a product of the matrix and the vector. So we'll define what that is, and then we'll go through an example and an example of how to do that. And then we're going to take that, we're going to take this idea and connect it to the idea of linear combinations. Okay, and then the last part of this section, we're going to talk about the solution of this system and how it connects to linear combinations and the idea of span and the pivots that are involved in our matrix. Okay, so there's a very nice theorem that actually connects all these ideas together. Okay. So let's first define what the matrix product is. So the matrix times a vector. Okay. All right. So before we do that, we need to set up some of our or state some of our assumptions. Okay, so if A is an m by n matrix, okay, remember that when we write in this order, m is the number of rows and n is the number of columns. Okay. And so we're assuming that A consists of columns, say, we're denoting those by A1, A2, all the way up to A sub n. Because A sub n, since we're assuming our matrix we're assuming that our matrix has n columns. Okay. All right, then the product of A times X is given as, so this is what we have. Okay, so we have basically a matrix that consists of column vectors. Okay, that's what these are acting as. And should go ahead, I'll go ahead and put some arrows on there just to indicate that that these are vectors. Okay, so the first column we have A1. Okay, so that is the notation representing, basically giving us or representing the column in the first, right, the vector in the first column. Okay, the next one we have is going to be, we have A2, okay, and then so on. Okay, so we do have other vectors or other column vectors involved. So that's what this dot 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 means. And then we just close that out. Okay. All right, so there's your there's our matrix, and then we have our vector. Okay. Let's go ahead and write that out here. Our vector X, okay, we're going to assume that the entries are going to be X1, X2, so on. Okay, now the number of entries in the vector are going to be the same as the number of columns. Okay. All right, and so we have our matrix here that consists of your column. That consists of column vectors, and then this is your, basically this is the vector X, okay? So we have matrix A and the vector X here. And when we multiply them together, we end up getting a vector, okay? And we're gonna call that B, okay? And so one other thing here, one other important thing to realize here is that, again, we're assuming that we're working with an n by n matrix, okay? So that means that there's m rows, okay, and n columns, okay? So we have m by n. This is n by n because there's n, right? We have n of these, and then there's just one column. So the one thing or one rule of thumb is that in order for this to happen, these values have to be equal. Okay, those values must be equal. Otherwise, we couldn't do this. Okay. The other thing to keep in mind, the other important thing is that, okay, the size of our output, in other words, the size of the vector B, is going to turn out to be an m by 1 vector. That's determined by this information. Okay. So these have to be equal, and the output, the size of the output vector is going to be an m by 1. And this is also going to hold true when we later talk about this, when we take a matrix and multiply it with another matrix. Okay. For now, just keep in mind that we're just talking about matrix times a vector. Okay, and then we can expand on this idea later. Okay, so that means, right, going back here, we have our vector B. Okay, so I'm just going to go ahead and write B here. Okay. In fact, well, maybe I can do it this way, more detailed. So this is going to consist of B1, B2, dot, 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 and then it's going to go up to B of M. Okay. Again, the vector B should have M entries. 1, 2, 3, 4, all the way up to M, because we have M number of rows here. Okay, that's what we're assuming. Okay. So rows, right, and N is columns. Okay. All right. Okay, so going back to some notation, okay, we say that this vector belongs to R of M. Okay, so we can say that more specifically, we can say that the vector B belongs to R sub M. So that just means that you're working with a vector with this in this what's called vector space. Okay, we'll get into vector space later on in the course. And over here we have X. X belongs to R of N. Okay, meaning that we're allowing for N number of entries. Okay. And the R, okay, the R just stands for, or basically is just to indicate that we are working with real values, okay, instead of complex values, all right? Okay, and these will become more important later on, okay, but that's just to kind of introduce some of the notation now, get that out of the way. All right, so how do we, okay, so then what does this really give us, okay? So we do get, so what are these basically in terms of what we have here? All right, let's take a closer look at this, okay? So it turns out, okay, that what this really means is that if we take x1, okay, so this is another way, so basically this is another way to write this out. So we have x1 times a1. In other words, so remember, each of these is a value, okay? All right, these are entries in the vector, okay? So x1, we take x1 and multiply it by a1, take x2, multiply it by a2, and then we continue to do that until we run out of values in here, okay? And then that, right? So basically all this is equal to the vector B. Okay. So this right here, this system, okay, that system or that equation is basically what this represents. Okay, it's a compact way of writing. Right, it's just a compact way of writing this out. Okay, so one thing you should recognize, and this was actually discussed in section 1.3, is that this is really saying that whatever this vector is can be written as a linear combination of a1, a2, all the way up to a sub n. Okay, and remember x1, x2, dot 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 x of n. Those are just numbers, right? Okay. In other words, another term for those is scalar values. Okay. All right. So there's various names for these. Another name, which is used in a lot of linear algebra books, is these are called the weights. Okay. And you'll see the significance of those later on. Okay. All right. So again, this vector B, right? Basically is represented as a linear combination of a1, a2, dot 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 a sub n. Okay, so let's write that out. Okay. Another way to state that is basically we can state this in terms of the idea of the span. So the vector B belongs to the span of these vectors, a1, a2, a of n. Okay. So these are basically interchangeable. Okay, so when we say a vector lives in a span of a collection of vectors, that just means that that vector can be represented as a linear combination of these vectors. Okay, so these are interchangeable. Okay, all right. So later on, we're going to actually connect all this. There's a really nice theorem that connects these together. Okay, all right. So let's go. Let's take this moment to do an example. Look at a specific example of this. Okay. So like I said, it's very important to understand a lot of the theorems in this chapter. Have to understand, right? You need to assume that the matrix is really just a storage for these column vectors. Okay, that is a way you need to start thinking about your matrices. Okay, so let's look at an example of this. So let's say we have the matrix 1, 2, -1, and 0, -5, and 3. And then we have our vector, okay, 4, 3, 7. And we want to figure out what this result is. Okay, so we're going to apply this definition. All right. So remember, when you have a matrix and you're multiplying by a vector, what you do is you take the first number, multiply it by the first column, the second one goes with the second column, and so on. So let's apply that here. Okay. So again, think of this, right? So here, okay, you have your first column, okay, which is right, for that vector, you have another vector and this vector. Okay. Okay. So this result, okay, in fact, I'm going to call this, let's call this A, and this is X. Now let's first check. It's always a good idea to check to see if these are compatible, right? So A is, since we have 2 rows and 3 columns, this is going to be 2 by 3. And this is going to be a 3 by 1. So the values, these inside values match. Okay. So we're good. Okay, we can definitely do this. Okay. And then the output, right? The size of the vector B that we're looking for, okay, this is B, is going to have basically 2 entries. Okay. So this turns out to be a 2 by 1. Okay, so 2, right? 2 by 1. Okay, let's go ahead and write this out. So number 4, right? Okay, so A times X is going to be 4 times the first column vector, okay, plus, okay, the next one, okay, is going to be, we have 3 times 2 and -5, okay, and then we have 7 times -1, 3. So again, all I did is take 4 times the first column, 3 times the second column, 7 times the third column. Okay. Okay. In fact, I'm going to straighten this out a little bit. Okay. All right. So doing this, right, doing these operations that was discussed, right? That is discussed in the previous section. Okay, so let's go through that. So this is going to give us 4, 0. Then we have 6, -15. Okay, so you just, again, that's a scalar. So you just distribute into each of the entries. Same thing with this one. So you get 3 times 2 is 6, 3 times -5 is -15. Okay. And then finally we have 7 times -1, which was -7. And then 7 times 3 is 21. Notice that we get 3 vectors of the same size, and basically we can combine those. Okay. All right. So we're going to get 4 plus 6 plus 7. That's going to give us basically 10 minus 7, which is 3. And then we have 0 minus 15, which is -15 plus 21. That will give us 6. Okay. Okay, and there's our that is our solution. Okay, so that is basically how you take a matrix and multiply another vector. Okay, all right, that is the formal way to do it. Now I know some of you have probably seen it done in a different way, and that way is using what's called the dot product. So you can use the dot product to come out with the same solution. However, to understand a lot of these theorems, especially early on, you really have to break, or sometimes you have to think about the matrix times a vector in this sense. And this is actually the more formal way to do it, especially when you get to more advanced coursework, or if you're doing more, or if you're going to more advanced classes. Okay. All right, let's do another one just for fun. Okay. Remember, the compatibility is an important issue. Okay, so let's go to the next example. All right, let's say we have, this time we have this matrix, okay? So we have a 3 by 2. So we have 2, -3, 8, 0, -5, 2. And we're going to take that matrix and multiply it by 4, 7. So we want to find out what that vector is, what the vector B is. Okay, let's take a careful look at the size of these. Okay. So this is 3 by 2. Okay. Again, 3 rows, 2 columns, always rows by columns. And then this is 2 by 1. So this is definitely compatible, right? These are equal, right? These are equal to each other. And also the result, right? The size of our output vector, or vector B, will be a 3 by 1. Okay. All right, so let's go ahead and solve this. So there's the first value that's going to correspond to the first column. Second value is going to correspond to the second column. So we're going to have 4 times. Okay. And again, I'm going to call this A. And I'll call this X. So A times X is going to be 4. So we have 4 times the first column of A plus 7 times the second column of A. Just like we did in the previous example. Okay. So again, 4, right, times the first column, okay, of A, and then 7 times the second column of A. This one, right, and then this one. Okay. Notice again, right, we have a 3 by 1 and another 3 by 1 here. So we can definitely add these together. Okay. So we're going to distribute the 4. Okay, so we get 8, 32, and minus 20. And then we have 7 times minus 3 is negative 21. 7 times 0 is 0. And then 7 times 2 is 14. Okay. Okay, and then we can go ahead and add these together. Okay. So we end up getting minus 13, 32, and negative 6. Okay. And there is our vector B. Okay. All right, so putting all this together, okay, basically what this is saying is that this vector, okay, that lives in R3, right, we have 3 entries here, so X, Y, Z, right? So this is just a coordinate, right? We can represent this as a coordinate in 3 dimensions. So this, and then you draw, basically if you take an arrow and draw it from the origin to this point, that gives you the vector. That tells you what this looks like, okay? So this vector can be represented, right, or can be expressed as a linear combination of this vector and this vector. So we say that this vector lives in the span of this vector and this vector, okay? Now, if you think about geometrically, what's going on here, right, is basically, if you look at this one and this one, okay, so you have, let's say this is V, let's say this is A1, this is A2, you have A1, right, and you have A2. Okay, and so when you basically put these together, okay, you basically form a plane. All right, okay, it gives you a plane, and in that plane, okay, lies this vector. Okay, lies this point. Okay, so this point, basically, you can say that this vector lives in the plane spanned by this vector and this vector. Okay, so we'll get a little bit more into that later on. Okay. All right. Okay, so let's continue with this. Okay. Okay, again, I want to reiterate that whatever the solution of this is, okay, right? If we're given, right, let's say we're given the matrix A and we're given the matrix, we're given the matrix A and we're given the vector B. And if there's a solution, okay, if there's a solution, that means that there's a vector X such that if you take that matrix A and multiply by this vector, then it gives us this vector B, okay? So if that's the case, right, if we're given this and we're given this, and if there's a solution, that means that this vector, right, can be represented as a linear combination of these column vectors, okay? Now, not every vector, we don't always have a solution. Not every vector has a solution, okay? And there's properties to determine this, okay? All right. All right, so let's summarize that idea in a theorem. Okay, here's a theorem that summarizes basically what I said earlier. So if A belongs to, and make sure here, we're working with an M by N, okay? So this notation just means that all it means is that we're letting A be a matrix that consists of real value entries. And that matrix is defined, basically the size of that matrix is M by N. So the number of rows is M, the number of columns is N. Okay, so that's all that notation really means. Okay, and as you know, probably already, mathematics there's a lot of notation involved. Okay. And because we're assuming our matrix has n columns, so that means that this matrix has that means we're going up to A sub n, right? N columns. And vector B, okay, the vector B is in R of M, okay? Again, going back to this idea, because we have M by N and this is N by 1, therefore this has to be an M by 1, okay? So that means our vector B is in R of M, okay? So the matrix equation, AX equals to B, has the same solution set as the vector equation. So exactly what I have here, okay? Right. Okay, so whatever the solution is here, okay, is going to be the solution of this one, okay? And this, remember, the solution to the system, so again, this is our matrix, right? This is our matrix equation. So whatever the solution to that is, the solution is these, basically referring to the solution vector. That's what these values are: x1, x2, dot, 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 and so up to x of n. Okay. Now, sometimes in some books, you may see this expressed as, you may see that expressed in this form. So this is another way that some books may write this. And this is using that augmented idea. Okay, so they'll write, they'll basically have A1, A1, A2, dot, 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 A sub n. And then you have a vertical line there, and then the vector B. So this is just a more compact way of writing this, but they all, right, they all mean the same, right? They all mean the same thing, okay? Just expressed in a different way. All right. And so again, okay, if there's a solution to this system, okay, that implies, okay, okay, that basically just that says that the vector B can be expressed as a linear combination, okay, of A1, A2, dot, dot, A sub n. So in other words, the vector B belongs to the span. A1, A2, and so on. Okay. Okay. And the span, okay, the idea, again, the idea of the span is just, goes back to the idea of the linear combination, okay? All right, let's look at another example here. Okay. Let's see. All right. All right, so let's take a look at this one. So we have the matrix contains 1, 3, and 4, and then -4, 2, and okay, -6, and then -3, -2, and -7. Okay. And let's define our vector B. So for that, we're going to say it consists of B1, B2, and B3. Okay. Okay. So there's our matrix A, and there's our matrix B. All right. So the question here is, is AX equal B consistent for all possible values of B1, B2, and B3? Okay, that is the question. Okay. And so this is basically similar to the span issue. So in other words, for what values, okay, for what values is this in the span of the vector in column 1, the vector in column 2, and the vector in column 3? Okay. Right. Okay, so let's write this out. Good, so this is what we have. Okay, so let's call this, again, just to be consistent with what I have over here. This is, right, we can say this is A1, A2, and A3. All right, so what we need to look at is, right, we have X1 times A1 plus X2 times A2 plus X3 times A3 equals to our vector B. Okay. So in other words, we need to see for which values does this equation hold true. Okay. So in order to answer this, what we need to do is we need to take this and augment it with the vector B and then go through our row operations. Okay. There's my matrix A, and then here I have B1, B2, and B3. Okay. So let's go through and put this into echelon form. Okay. All right. All right. So what we can do is, since I have a minus, so remember the goal is to make this 0, this one 0, and this is 0. So to make that 0, I'm going to take 4 times this value and add it to this one. Okay. So we have 4 times row 1. Add it to row 2, and then store that result in row 2. Okay, remember, whatever I do to this one, I have to do for each of these values to keep the system the same. And going back here, remember, consistent means that there is a solution, whether it's a unique solution or there's an infinitely many solutions. Okay. Okay, so we're going to have 0 here. Okay, we have 12 and 2. 12 and 2, what is that? 14, right? And then we have 4 times 4, 16. 16 minus 6, that's going to give us 10. And then we get here, I have to widen this a little bit. So we got 4 times B1 plus B2. Okay, again, 4 times this plus this. Right? And then we need to get this 0. So let's go ahead and do the same step, which is fine. Okay, so we got 3 times, I need to get this 0, so I multiply this by 3. So we have 3 times row 1 plus row 3 and store that result in row 3. So we're going to get 0 there. 3, right? 3 times 1 is 3, minus 3 is 0. Then we get 9. 9 minus 2 is going to be 7. And then we get 12 minus 7. And that's going to give us what? That's going to give us basically 5, right? Yeah. Okay. And then we have 4 times B1 plus B3. All righty. Okay. All right, one more step here. And that is, right, we need to make this 0. So what we can do is we can say 1/2 of 14, or sorry, negative 1/2 of 14, right? That will give us negative 7, and we add to 7, then we get 0. Okay. So minus 1/2, row 2, we add it to row 3 and then store the result in row 3. So we get 0 here, 0. 1/2 of 10, negative 1/2 of 10 is -5. -5 plus 5 is going to give us 0. And then to make some more space here. And then we have minus 1/2 times 4b1, okay, plus b2 plus 4 times b1, okay, I'm sorry, plus 4 times b1 plus b3, okay. Okay, all right, let's see. Okay. All right, let's see. Okay. Oh, I think this should be 3, sorry, that's my bad. So when I went from here, so that's 3 times b1 plus b3. Okay, so that should be 3 there. Okay, so then, okay, so I need some more space here. Okay, so we're going to end up getting, right, minus 1/2 of this. Okay, so this is going to be minus 1/2 of 4b1 plus b2 plus 3b1 plus b3. Okay, there we go. Okay, notice, right, we have this in, right, this is in row echelon form, but not quite in reduced row echelon form. So this is good enough for what we need, okay? Now what we can do is we can shift our attention to what's happening here, okay? Look at this part, okay, right here. Okay. All right. So look at that part. So this is going to be it. This is going to be the key to answering this question. Okay. So it turns out, right? Remember that we're interested in seeing, right? Okay. We're interested in seeing, is this system consistent for all possible values of B1, B2, and B3? Okay? Now look here. Okay. If this, right, there are values, there exist values, right, B1, B2, B1, B2, and B3, such that if you plug in here, you will get 0. If that's the case, then this system is consistent. If not, right, if this is not equal to 0, right, when you plug those in, then you get some number here besides 0, right, and therefore it's inconsistent, okay, because 0 times some number is going to be 0, right? Okay. Okay, so let's summarize that here. Okay, let's go back over here. All right. So let's summarize this. Okay, so first thing we notice, right, this is not consistent for every value, of the vector B, okay? More specifically, not consistent for every vector B, okay? And I mentioned that in the beginning. I said that if you have a system AX equals B, it may not always have a solution, okay? All right. Why is that? Okay, so it's not consistent for every vector B since, okay, right, we can find there exist, okay, B1, B2, and B3 such that, right, such that minus 1/2 of 4 times B1 plus B2 plus 3 times B1 plus B3 is equal to 0, is not equal, I should say not equal to 0. Okay. Right. Again, it's not hard to find, right? It's easy, it's relatively easy to see that there are values, okay, that will not give us 0 here. Okay, if that's the case, like let's say for example, we get the number 4, right? So you get 0, 0, 0, and then 4 here. Well, obviously there's right, there's no values of x1 and x2 and x3 that make that happen. Okay. All right. Okay, so this actually demonstrates this example actually demonstrates something a little bit more, particularly with the pivot positions. Now, if you notice here, going back here, if you look at your pivots and you look at those leading entries, you get basically only have 2 of them, okay, all right, for this coefficient matrix. And that basically is telling us something, okay? And basically, and that's kind of why we don't have a solution, right? That's why we don't have this system for this particular matrix doesn't have a solution for every possible values of B1, B2, and B3. So this results, right? So we can, so this is a great, this will provide us a segue into the next theorem, and that is this one right here. So the next theorem will basically relate all these ideas together. Okay. And one other thing I do want to mention here, okay. So because of this, because there's only 2 pivots here, okay. The columns of A from this, based on this work here, okay, the columns of A don't form a span, right? Right? They don't span R3 in this case, right? R of R in this case R3. What does that mean? All that means is that, okay, remember this is living in R3, right? Okay. All that means is that that these columns, right, for whatever this is, it's not possible to find a solution for every vector B. And so then we say that the columns of A don't span R3. Okay. All right. So meaning, again, all that means is that for if they did span, okay, that would mean that every vector B, no matter what these entries are, you could find a solution for this corresponding matrix, for this corresponding coefficient matrix. Okay. Although in this case we don't, right? As we showed here. And that is because, right? Because we only get 2 pivots here, right? Instead of 3 pivots. If we had 3 pivots here, okay, if there was a number here, then the columns of A, right? The columns of A would span R3, meaning that you pick any vector in R3, you can find a linear combination of these vectors, A1, A2, and A3. Okay, so that's what we're going to summarize. All right, that's what we're going to state in the next theorem. Okay. Okay. All right, so let's assume, okay, let A belong to R of M by N. We have, so again, that just means that we have a matrix with entries or with real value entries, where the matrix has M rows and N number of columns, okay? So one thing in this course, a lot of these statements are, so the way this theorem works is that if one statement is true, then automatically the other statements are true. And that's kind of what this circular logical, what this logical statement means here. And so in other words, if one of these, right? So if one of these is true, okay, as I'll write out in a few minutes, then they're all true. If one is false, then they're all false, okay? So here they are, okay? So the statements are all, so these statements are equivalent. All right, first statement. So this also summarizes what we've talked about, okay? So for each, in other words, for every vector B, R of M, okay, AX equals to B. Okay, so it has a solution, okay? Again, that is just a statement, right? So if that's true, if that statement is true, then the next following statements are automatically true, okay? So that would imply that each vector B and R of M, okay, is a linear, right? So again, going back to what we did earlier, if there's a solution for this vector, that means that this vector B can be written as a linear combination of the columns of A. That's exactly what the next, what this statement 2 is going to say here. Okay, so again, so if the first statement is true, okay, then automatically we can say that that vector B, okay, and again, B lives in R sub M, okay, all right, going back to, okay, let's find that here. So there's our matrix A, right? And there is your vector. That's our, basically holds the weights that is represented by X. And then we have M by 1. Okay. So B, right, belongs to R of M. So if this has a solution, then therefore that vector B is a linear combination of the columns of A. That's exactly what we talked about earlier, okay? All right. So again, this is sort of just a nice summary that is in the form of a theorem. Okay. All right. Then the third statement says that the columns of A columns of the matrix A span R of M. Not M, not N, but M, right? Okay, M. Columns of A span R of M. Well, that's exactly what we illustrated here. So if there's a solution, okay, if there's a solution, right, or whichever one, if you think of it this way or this way. So if there's a solution to your system, that means that the columns of that matrix span R of M because, right, there's a solution here, okay? For every vector B, right, so for every vector B, if there's a solution, that means you can write that vector in terms of a linear combination. And so therefore we say that the columns of the columns, right, the vector columns of A span R of M. In other words, right, if this is true, okay, and then again, the wording is important for every vector in R of M, okay? So the columns of A span R of M. That just means if I choose any vector in R of M, okay, and if this is the case, that means that basically that vector is in the span, right? Okay, that vector is in the span of the columns, okay? That's what that means. So that's what this statement means. The columns of A span R of M. Again, you pick any vector, okay? If these are true, then you pick any vector in R of M can be written as a linear combination, okay? That's exactly what this means, okay? Now going back to this example, you can see in this case, for this matrix, okay, for these particular column vectors, that's not the case, right? These columns don't span R of, right? They don't span R of 3 because we found some values, right? We found some values B1 and B2, B1, B2, and B3 that don't give us a solution, okay? And this is the proof of it, okay? This is the justification, all right? Okay, the fourth statement. The fourth statement has to do with the pivots, okay? All right. Okay. So if one of these is true, they're all true. So A has a pivot position in every row. And that should make sense at the intuitive level, right? Because again, it goes back to this idea. Just go back to this. How many pivots we have? Well, we only have 2, whereas we have 3 rows. So because of that, that automatically tells us that, right, that we're not going to get a solution, right, for this particular matrix. We're not going to get a solution for every possible vector B. If we had, right, and again, when we say pivot, we're referring, remember, it has to be a non-zero value, okay? So if we had a non-zero value there, then we can say that every vector B, right, has a solution for this matrix. Okay. All right. So again, the key is that these are all right. All these statements are equivalent to each other, meaning that let's say if 3 is true, then 1, 2, 4 is true. If 4 is true, 3, 2, and 1 is true. If 1 is true, 2, 3, and 4 is true. If 4 is true, 3, 2, 1 is true. Okay. If one of these is false, they're all false. Okay. So they're either all true or they're all false. Okay. None in between. So you can't have 1 is true and 1 is false. Okay. So these are what's called logical statements. They're all logically equivalent to each other. Okay. All right. And so going back, sometimes you'll see this theorem in some textbooks. They'll write it out this way. They'll basically put numbers to this. Okay, so they'll say, okay, 1, right? Linear combinations for the second one, span was for the third one, and pivots was for the fourth one. So again, 3 is true, right? If 3 is true, that means 1 is true. Okay, by association, right? If 1 is true, 3 is true. If 4 is true, 2 is true. If 2 is true, 4 is true. So it works like that. Okay. So this is what's called a logical diagram. Okay, and these are you can find all these throughout math. Okay, especially at the more advanced coursework or the more advanced courses. And so then, with that said, as we progress, we're going to be adding on to this list because there's definitely more here. Okay, when we get to chapter 2, that's when we start to add. We'll begin to add more to this list. Okay. All right. All right. So let's see what else. Okay. Okay. Let's see. All right, there is one more theorem that I want to state here, and then basically that's the end of this section. So I want to, let's see, I can go ahead and state that here. Okay, like I said, linear algebra is full of theorems and and these kind of statements. Okay. So when you're reading, right, so it's always important to read, try to read what's in the book. And really, when you're doing the problems, try to, not only understand the, not only understand the calculation, but understand why is it that you're getting that result. Okay, if you can do that, if you can tie those ideas together, you'll make linear algebra a more enjoyable course. Okay, and you'll get a lot more out of it than just basically just cranking out problems. Okay. Okay, next theorem, or the last theorem for this section, but certainly not the last theorem of the course. Again, we're assuming that A is our matrix with real entries. And the vectors U and V belong to R of n. Now again, this is just, this is basically just a vector space. We'll get to that in chapter 4. Okay. All right, so U and V are vectors that belong to R of n. So for right now, okay, assume that this just means, we're just assuming that the vectors U and V have n number of entries. Okay. And we have C, which is just a real value, basically just a scalar. Okay. Okay. Okay, then, the first statement, okay, first statement is that if you take this matrix A and you operate on this, okay, remember these are vectors. So then this is the same as taking the matrix A and multiplied by U, and then taking this matrix and multiplied by V. So this is just the distributive property. And you can certainly do this for more than two vectors. If you have U, V, and W, then you can get A times U plus A times V plus A times W, okay? All right. And this is compatible because we're assuming that A is m by n. Okay. This is m by n, okay? And when you add these two, because they're the same, they're the same size, so when you add them together, you get n by 1. So this is compatible, right? These are matching values. And over here, this is going to be, you have m by n and n by 1. So this is going to be an m by 1, and this will be an m by 1 as well. Okay. So the result, when you add these two vectors, these are both m by 1, so the result will be n by 1, and that's the same as you get over here, right? This gives you an m by 1. So m and then 1 here, okay? Right. So it makes sense logically, right? So it's good that we have this property, okay? All right, the second statement is related to the scalar. All right. And that is, if we have A times C times U, okay, and U is the vector we're assuming. So what this says is that we can take the scalar outside. So you can take All right, so the way to think about this is you have a scalar times a vector, that's going to give us a vector. And then this matrix times a vector will give us a vector. And then over here, right, this is the same as taking the matrix times a vector, that will give us a vector, and then we distribute the scalar within that vector. So yes, it makes sense, okay, that we can do this. We can always move the scalars around. In fact, you can furthermore, you can say like this. Okay, but normally we don't write like that. Okay, but it's still fine. Okay, so let's just check the sizes here. Right, so this is m by n. That's what we're assuming. Okay, this is going to be, remember, scalar times a vector. U is an n by 1, so this is going to give us m by 1 here. Okay. By the way, scalar is just 1 by 1. Okay, right? It's just a simple 1 by 1. You can think of it as a 1 by 1 matrix. Okay. Okay. Although we don't really refer it like that. Okay. A times U, that's a matrix, right? This is m by n. U is n by 1. So this result's going to give us an m by 1. So therefore, right, we get m by 1. And then same kind of idea here. Okay. All right. So these two statements are quite useful for when we get to what's called linear transformations. Okay. All right. So so that is, I believe, I covered all the important points of section 4. I think out of everything that I've talked about, this theorem is like the most important. Okay. Be sure you understand this theorem and know how to work with it. Okay, because it is going to, we're going to look at some other ideas that kind of relate to this, or that I should say that are related to this. For example, linearly independence. Okay, that is another way to tell basically whether or not, specifically if we have what's called a homogeneous system, and if we know, right, if we know that the vectors are linearly independent of each other, then that tells us basically that we have a unique solution for our homogeneous system. Okay, so we'll get to that later on. Okay? But for now, try to understand this. Okay, and again, if one of these is true, these are all true. If one of these is false, they're all false. Okay, so I go ahead and stop here, and then I'll see you all next time.